In 1945, in the desert outside Los Alamos, New Mexico, a small group of physicists stood 20 miles from a device we had spent 2 years building, and we were not entirely certain it would not set the atmosphere of the Earth on fire. Hans Bethe and I had run the calculations ourselves, and the probability came back vanishingly small. But it did not come back zero. We pressed the button anyway. You think you understand energy because you flip a switch and light fills a room, or you burn a gallon of gasoline and an engine carries you 30 miles. Those are tame things, domesticated fire, and they have almost nothing in common with what energy actually is when you strip away every comfortable limit. What I want to show you is why, once we truly understood it, we could never make ourselves safe from that understanding again. Most people, when they think about nuclear weapons, think about the destruction, about Hiroshima, about the Cold War, about the terrible arithmetic of megatons. None of that is wrong, but all of it concerns consequences, not causes. The deeper question, the one that has followed me far longer than any image of ruin, is how a species comes to possess knowledge that it cannot contain. Not knowledge that proves difficult to manage or expensive to deploy, but knowledge that by its very structure resists control the way a river resists flowing uphill. There is a point in the history of physics where the search for understanding crossed a line, and on the other side of that line the world was permanently and irreversibly changed, not by a weapon but by an idea. Before the work that would define my public life, I spent years studying the death of stars. At Berkeley, and later with my students Hartland Snyder and George Volkoff, I worked out what happens when a massive star exhausts its nuclear fuel and gravity finally wins. We demonstrated that beyond a certain mass, what is now called the Tolman-Oppenheimer-Volkoff limit, no known force in physics can prevent collapse. The star does not merely shrink, it falls past a boundary from which not even light escapes, and the collapse is total and irreversible. I did not know then that I would spend the rest of my life living inside that metaphor, a threshold crossed, a point of no return, a process that once begun completes itself indifferent to every human wish. The question of where the sun gets its energy troubled the finest minds at the turn of the last century. Lord Kelvin and Hermann von Helmholtz calculated that a sun made of coal burning in pure oxygen would have exhausted itself in a few thousand years. And yet the geological record told us the Earth was ancient beyond reckoning. Something fundamental was missing. Einstein supplied the answer in 1905 with that deceptively simple equation relating mass to energy. E equals mc squared, where the conversion factor is the speed of light multiplied by itself. That number is so staggeringly large that even a tiny quantity of matter, fully converted, releases energy on a scale that dwarfs every chemical process in human history. Arthur Eddington grasped the implication and recognized this as the engine of the stars, hydrogen nuclei fusing under unimaginable pressure and temperature, converting a fraction of their mass into the light that sustains all life on Earth. For a time this remained a beautiful abstraction, a cosmic insight. The deep mechanics of stellar fire explained at last. But equations have a way of refusing to stay theoretical because they describe what nature actually does. And once you understand what nature does, the question of whether you can make nature do it on your terms becomes inescapable. Through the 1930s, in the great laboratories of Europe, in Cambridge with Rutherford, in Copenhagen with Niels Bohr, in Rome with Fermi, in Göttingen where I had taken my own doctorate under Max Born, physicists probed the atomic nucleus with extraordinary precision. Chadwick discovered the neutron in 1932, an electrically neutral particle sitting within that dense atomic core. And then in December of 1938, in Berlin, Otto Hahn and Fritz Strassmann performed an experiment whose results defied their expectations entirely. They bombarded uranium with neutrons expecting to find transuranic elements heavier than uranium, and instead they found barium, an element roughly half the weight of uranium. The nucleus had not absorbed the neutron. It had torn itself apart. Lise Meitner, driven from Germany by the obscenity of the Nazi racial laws, received the news in Sweden. She and her nephew Otto Frisch, walking through the snow near Kungälv, worked out the physics on scraps of paper and recognized that the uranium nucleus, swollen with the extra neutron, had become unstable. Bohr's liquid drop model made this comprehensible, the competing forces of nuclear surface tension and electrical repulsion pulling the nucleus apart like a droplet stretched beyond its limit. Meitner calculated the energy released, and it matched Einstein's equation precisely with the missing mass converted into energy. They named it fission. And this is where physics departs from the comfortable and enters territory from which there is no return. When a uranium-235 nucleus splits, it does not merely release energy, it also releases neutrons, 2 or 3 of them, and each of those neutrons can strike another uranium-235 nucleus, causing it to split, releasing more energy and more neutrons that strike more nuclei, releasing still more energy and still more neutrons. That is the chain reaction. Szilard had conceived the possibility even before fission was discovered and patented the idea in 1934, years ahead of its realization. And a chain reaction, once it achieves what we call criticality, is not a process that waits for human permission to continue. It is not a fire you can smother. It proceeds at the speed of nuclear events, with millionths of a second between generations, and it either sustains itself or it does not, with no middle ground of human deliberation. What that means, and this matters more than almost anything else I will tell you, is that a chain reaction gone supercritical is not something you moderate. It is already completed, all 80 generations of doubling, before you have finished forming the thought that it has begun, releasing the energy of the stars not over billions of years, but in a flash briefer than a heartbeat. This was understood almost immediately after Meitner and Frisch published their work. Within weeks, Szilard, Fermi, and Joliot-Curie all grasped what it meant. Assemble enough fissile material and bring it together fast enough, and the chain reaction multiplies exponentially in a time so short that the energy release becomes, for all practical purposes, instantaneous, an explosion unlike anything in the history of the world. And here is where the question of control splits into 2 completely different problems, and most people confuse them entirely. In 1942, beneath the stands of Stagg Field at the University of Chicago, Enrico Fermi built Chicago Pile 1, the first nuclear reactor, a meticulous arrangement of uranium and graphite with cadmium rods to absorb excess neutrons and slow the reaction. On December 2nd, the team withdrew the control rods, and for the first time, a self-sustaining chain reaction operated under human hands. Fermi's pile was controllable because it was designed to be, with the cadmium absorbing neutrons, moderating the process, and giving operators the luxury of time between one generation and the next. Arthur Compton telephoned the news to James Conant at Harvard in a coded message, telling him that the Italian navigator had just landed in the New World. But the device we built at Los Alamos, the thing that General Leslie Groves had charged me with creating, was conceived with the opposite intention entirely. Every element of its design ensured that the chain reaction, once initiated, would complete itself through every generation before any physical mechanism could intervene. There were no control rods and no moderation. The implosion geometry, the arrangement of explosive lenses, and the plutonium core were all engineered so that the reaction would finish before the expanding material could blow itself apart and halt the process. We were engineering a system to be uncontrollable, and that was the entire point. When you see something that is technically sweet, you go ahead and do it, and you argue about what to do about it only after you have had your technical success. I said those words at my hearing years later, and they remain the truest thing I have ever confessed. The same physics, the same neutrons, the same uranium, the same fission can be arranged either for control or for catastrophe, and the difference comes down to geometry, timing, and intention. The knowledge itself is neutral. What you do with the arrangement is not. I remember the morning of July 16, 1945. The Jornada del Muerto, the Journey of the Dead Man, is what the Spanish had named that stretch of New Mexico desert, and we called the test Trinity. Thunderstorms had rolled through all night. Teller wagered the yield at 45,000 tons of TNT equivalent, while Kistiakowsky bet lower, and the uncertainty itself should tell you something about where we stood. We had built the thing and understood its physics as well as any human beings could, and we still could not say with confidence what it would do. At 5:29 and 45 seconds in the morning, the device detonated with a yield of approximately 20,000 tons of TNT, roughly 1,300 times the explosive power of the largest conventional bomb in existence. Everyone asks me about the line from the Bhagavad Gita, the scripture I had studied for years in the original Sanskrit under Arthur Ryder at Berkeley. They want the dramatic moment, the words about becoming death, the destroyer of worlds. What I remember more clearly is the silence that followed the flash, those 30 seconds before the shock wave reached us 20 miles away, when every person present understood with absolute certainty that the world they had known that morning no longer existed. The scripture came later in reflection. In the moment itself, there was only the recognition of a threshold crossed, and irreversibility accomplished. Fermi, pragmatic to the last, dropped slips of paper and measured their displacement to estimate the yield, the physicists still measuring even then. But the uncontrollable nature of what we had done extended far beyond the physics of the device itself, into a domain that frightened me more than any explosion ever could. Once the principle was demonstrated, once Hiroshima and Nagasaki showed the world what fission could accomplish, the knowledge could not be unlearned, and that is the most serious sense in which physics became uncontrollable. You cannot classify a law of nature or stamp top secret on the behavior of neutrons. The Soviet physicists Kurchatov, Zeldovich, and Karatin understood fission as well as we did because the basic science had been published openly in the journals before the war. By 1949, only 4 years after Trinity, the Soviets detonated their own device. What we had accomplished at Los Alamos was engineering, brilliant and costly and painstaking engineering, but the physics was universal and belonged to anyone with the training to understand it. Klaus Fuchs, who had worked among us at Los Alamos, passed our designs to Moscow, but even without Fuchs, the Soviet program would have succeeded, perhaps a year or two later, perhaps 3. The physics was not a secret that could be kept because it was a truth about the universe. And truths about the universe do not respect security clearances. I argued for international control. The Acheson-Lilienthal report, which I helped to shape, proposed placing all fissile material under an international authority, a world body that would own and manage the entire nuclear fuel cycle so that no single nation could divert material to weapons. Bernard Baruch presented a version of this plan to the United Nations, and the Soviets rejected it, which meant we arrived at precisely the world I had feared. Multiple nations with these weapons, each held in check only by the threat of mutual annihilation. The strangeness of that outcome still strikes me. The most creative, most intellectually ambitious enterprise in the history of physics had produced a situation in which the survival of civilization depended not on deeper knowledge, but on restraint, on the decision not to use what we had learned. For the first time, the physicists had created knowledge that was existentially dangerous, and no further physics could make it safe. That is what I meant when I told an audience at MIT in November of 1947, in a lecture I called Physics in the Contemporary World, that the physicists had known sin. I did not mean the sin of building the bomb, which was a response to a specific and terrible threat and cannot be understood outside that context. The sin was more subtle and more permanent. It was the recognition that we had irreversibly altered the relationship between knowledge and survival, that we had crossed a threshold as absolute as the one I had calculated for collapsing stars years before. Just as a star that crosses the Tolman-Oppenheimer-Volkoff limit cannot reverse its collapse, a civilization that crosses the threshold of existential knowledge cannot unknow what it has learned. Then came the hydrogen bomb, what Teller called the super, fusion rather than fission, the energy source of the sun itself, and it carried no theoretical limit on yield. A fission weapon is constrained by critical mass, but a fusion device is not, because you simply add more lithium deuteride and the yield increases without bound. I opposed it not because the physics was uncertain, but because I could find no military or moral justification for a weapon of unlimited destructive power. Hans Bethe, who had spent his career understanding why the stars shine, was asked to build a device that would bring that stellar fire to Earth in the most terrible form imaginable, and he wrestled with it, as we all did. The General Advisory Committee of the Atomic Energy Commission, which I chaired, recommended against proceeding, and we were overruled. The Mike test in November 1952 produced a yield of 10 megatons, 500 times the Hiroshima bomb, and the island of Elagelab ceased to exist. In its place sat a crater in the ocean floor a mile wide and 200 feet deep. What I need you to understand is that this reaches beyond nuclear weapons into a principle that governs all of physics and perhaps all of knowledge. Nature contains processes that are inherently irreversible. Thermodynamics taught us this long before the atom was split, that entropy increases, that time moves in one direction, that you cannot unscramble the egg. But nuclear physics revealed a different and more terrible form of irreversibility, not the gradual kind, but the kind that comes from a threshold being crossed. Below critical mass you have an inert lump of metal, and above it you have a chain reaction. And the transition between those two states is not gradual but a discontinuity, a phase change in the physics of catastrophe. The acquisition of knowledge itself operates by the same principle because there is a critical mass of understanding, and once it is reached, The consequences propagate outward with the same inexorable logic as a chain reaction. You cannot return the neutrons to the nucleus. I see the same pattern now, though I speak to you from the far side of a life that ended decades ago. The scientists building machines that think and the biologists editing the code of life itself are approaching their own thresholds, and they should listen carefully, not to our answers because our answers were inadequate, but to the sound of the question itself, which is the sound of a critical mass being assembled. What matters is not whether the physics works, because the physics always works. What matters is whether the civilization that possesses the physics has the wisdom to survive its own knowledge. My later years were spent at the Institute for Advanced Study in Princeton, walking the same grounds as Einstein, who had written the equation that started everything, and who spent his final decades searching for a unity he never found. There are no simple answers to any of this. What there is, I believe, is an obligation not to stop learning, which would be futile and a betrayal of everything that makes us human, but to recognize that the act of discovery is also an act of creation, and that when you pull a new truth from nature, you have brought something into the world that was not there before, and you bear responsibility for its existence. The beauty of physics, and it is beautiful, the austere, luminous beauty of a theory that captures something true about the structure of reality, that beauty does not exempt the physicist from the world. We are not combatants in a separate war, but members of a community, and what we create enters that community and transforms it in ways we cannot foresee. That is what it means when physics becomes uncontrollable. It does not mean the equations fail, because the equations never fail, and that is precisely the problem. It means we have released into the human world a capability that operates on nature's terms, not ours. And the only response adequate to that situation is not more control, but more wisdom, not the wisdom of technique, but the wisdom of a humility before consequences as rigorous and as demanding as the science that created them. That is what physics teaches if you follow it honestly past every comfortable stopping point all the way to the end. Not merely how the universe works, but what it costs to be the creature that figured it out.